Yes.
Good morning, everyone, and welcome to the P and Applied Mathematics Seminar. It's a pleasure for me to open session 93 of the seminar. Today we have two excellent speakers, Jacque Simon and Maher Moaker. Introducing Jacque Simon, we have to Professor Roberto Capistrano. Thank you, Roberto. You can start.
Thank you. Thank you. Hi, everyone. Good afternoon. Well, it's a pleasure for our seminar to welcome Professor Jacque Simon, Honorary Director of Research at CNRS, France. And before he starts, let me give some words about the career of Professor Simon. Okay. Professor Simon graduated from École Polytechnique in Paris in 70 and got his PhD in Paris as well, 77, under the supervision of Jacques William. Professor Simon had several positions, for example, Jacques William Laboratory, Paris 6, Blaise Pascal University, University of Seville, University of Nice, and others. Okay, and Professor Simon, like the research of him is in functional analysis, nonlinear PDEs, domain variation, and modeling like, for example, shallow water and problems, okay? It's important to point out that Professor Simon has more than 9,000 citations in more than 80 publications between books and articles. And one of his work is one of the more important paper in math, compact sets in the space LP, with more than 5,000 citations and widely used in several problems. Today, Professor Simon will give us this great opportunity to attend his lecture, Integration with Values in Neumann Space for PDEs. Thank you, Professor, for this nice opportunity.
Okay, I start. I don't. Yes. Okay. I will speak from integration with values in a Neumann space, and the question I will go the plan first. The first thing that is what is a Neumann space. We will see that. Then we will give some example of Neumann space. For example, LP, LP lock, WMP, LP weak, L infinity star weak are Neumann spaces. We will see some example of application to PDEs, to the heat equation, to the Navier-Stokes equation, and to a stochastic equation. And then we construct all the space with value in a Neumann space that occurs in PDE. These are the space of distribution, the space of measure, the space LP, and the space WMP. Then we will compare what is an integral measure that is new, that is my invention maybe, with a classical class of measurable function, of almost equal measurable function. We will compare the two and we will see that they are the same when the both are defined, but the domain of definition is not exactly the same. We will see then what we can do if E is not a Neumann space. And I will give, if I have time, a hint for the proof of the existence of integral measure, the existence of LP. This is a crucial point. So we go first, well, what is a Neumann space? A Neumann space is a semi-norm, separated, sequentially completed space. And so what are that? What is that? Semi-norm mean that the space is equipped with a lot of semi-norms. The semi-norms are written here, and the set of semi-norms is not necessarily a sequence. It is everything, but this is equivalent to a locally convex topological vector space. That is an old theorem of von Neumann. Separated means that 0 is the only element that cancel all the seminorms. So, and so, okay. And sequentially complete means that every Cauchy sequence is convergent. And so what is a Cauchy sequence? A Cauchy sequence UN means that UM minus UN in seminorm of index nu, and the supremum for M greater than N goes to 0 as N goes to infinity. If you have only a norm, not a seminorm, it is the usual definition of a Cauchy sequence. And if you have a lot of seminorms, it is a seminorm, it is a Cauchy sequence for each seminorm. That it functions as for Banach spaces. And in a Neumann space, there is a limit. So UN minus U goes to 0 for all seminorms. Okay. And now we will define the space LP on lambda. Lambda is an open set of Rn with values in E, where E is a Neumann space, and C application to PDEs. So the example of Neumann space. The first Neumann space is the LP space, and W, the Lebesgue space and the Sobolev space are Neumann space because every Banach space is a Neumann space. The local space LP loc are again Neumann space because they are Fréchet space for these seminorms. And every Fréchet space is a Neumann space. And the space WMP and again WMP loc are again Neumann space. And again the local Sobolev space WMP loc are Neumann space. Other space, a little more complicated, are space LP weak. That means that LP, which is indexed, which is equipped with a seminorm, indexed by some function G, and it is the seminorms are written here. And this follow that a reason, I will give you the reference at the end. If a space is reflexive, then A and E weak are Neumann space, or LP is reflective, so it is a Neumann space. But it can be noticed that it is sequentially complete, but it is not complete. That is, the Cauchy filters are not converging. And it is a general result of that can be found in Schaeffer, that space, merde, I don't remember the word. Okay, that the space are not complete. Okay, H1 and other space are not complete. They are only sequentially complete. And another space, which is a Neumann space, is a space L infinity star weak, and all the Sobolev with the seminorm star weak are Sobolev spaces. And this is again proved in the book of integration that is on press. And the same result holds for the Sobolev spaces WMP weak and WM infinity star weak. So I forget. Well, and many other space are Neumann space. The distribution, the set of the test function D of omega, the measure, the set of uniformly continuous function with compact support, and all closed or sequentially closed subset of Neumann space are Neumann spaces. So it's a very large class. And now we see some application. If you find a solution of the heat equation in an unbounded and unregular domain. So this is there, and the theorem says that in this case, where the right-hand side is only L2 in H-1, and if we have a function g such that delta g and dg over dt are in L2 log and in L2 of 0t with values in H-1 log, and if U0 is in H-1 log, and if we find for U0 minus G0 in L2 the omega, then there exists a unique solution which is in L2 of H1 log and which is continuous in values in H-1 log. So here we have something that happens in Neumann space, which is the H-1 log. Okay. The other thing is the Leray-Hopf theorem for the Navier-Stokes equation. V and H are the closure of this subset. This is classic. We consider this, and that we find a solution U in L2 of 0t V and in L infinity in 0t H, and it is continuous in H weak, okay? And the pressure gradient of P is with value in H gradient of P as value in W minus 1 infinity of 0t with values in H1 in H minus 1 of omega cube. So it is again in this kind of space, which you cannot find if you only consider spaces with values in a Banach space. Yes, but it is written here. Sorry. And the proof is equally slightly easier if you use fixed point theorem in that space. The normal proof. And the third application, which is a little more complicated, is in a stochastic equation, and it is done by Dronio and Allied. And he uses a space that he called LR of 0t in L2 weak, which is a usual space LR with value in L2, but which is endowed with the weakest topology that made this application continuous. And in fact, this is the space that I define, which is the space L2 of 0t in L2 weak. But he use a complicated definition because he don't know how to construct this space. So we will see how to contract these spaces. The first space is the distribution. The distribution is quite classical if we consider Schwarz theorem with the vector values. They are the continuous map from D to omega into E, but I use the seminorms indexed by Q, where Q is a positive continuous functions, and this is the value of the seminorms. They make the D of omega a Neumann space, and in fact, this defines the inductive limit. So it is the same thing as Schwarz do for the space D. And for D prime, he is provided with the seminorms indexed by phi and by nu, which is the seminorms on D prime indexed by phi nu is F applied to phi in seminorm nu. And these seminorms may d prime of omega to u a Neumann space, and this is the simple topology, which is weaker than the topology of Schwarz, which is the hard topology, or the strong topology, sorry. But it has the same weak convergence sequences, the same bounded sets, the same compact sets, the same sequentially continuous application. The only thing that differ is the continuous functions that are not the same. But it is easier to use, and it is more general because it is used a weak topology that is larger than a strong one. And so if we want to include it in a lot of things, it is better to use this topology. Because Schwarz consider either space that are complete, but this is not the case of HM weak, as we see, or quasi-complete, but this is more restrictive than Neumann, or only separated, but this is not satisfactory because we cannot identify a continuous function with distribution in that case. There is only thing really useful to know, that is the theorem that say the space D prime construct on omega 1 times omega 2 is the same than D prime on omega 1 with value in D prime of omega 2. And this is a bijection continuous, sequentially continuous, and its inverse is sequentially continuous, linear. And this is proved in one of my books. So now, with the distribution, we intend to construct the space of measure and the space with LP and the space W minus NP and W NP. And so the measure is the space of linear continuous function from K into E, where K is the continuous function with compact support, provided with these seminorms. And this is the Neumann space. And these seminorms define the topology of inductive limit, because the topology of inductive limit is a little more difficult to use, but it is the same topology, in fact. And the measure is provided with the seminorms of the weak topology of the measure. And this topology makes the measure a Neumann space. And this is proved in the book of integration that is in press, and which will be available in some months. Okay, now we will define the space LP with value in E, and this is maybe a crucial point. First, we consider a function f, which is in the space B of omega into E, which are uniformly continuous functions and that are null outside bounded set. And we define the integral as the limit of Sn of f, and where Sn of f is, you consider this partition of the domain with small cubes, and you consider the value at the center of the cube, and you go and you multiply it by the measure of every cube, and you go n to infinity, so the number of cube is going to infinity, and it converges. It's easy to see. So we can integrate easily a continuous function, and we will define LP as the limit of continuous function. of uniformly considered function. So we say that a measure f is p integrable if it is if there is a sequence of fn in B of omega 2 with value in A, such that fn goes to f in the space of measure, first condition, and the second condition, if P is finished, it is a Cauchy sequence for each semi-norms for the integral with of the power of P. And such a sequence is said to be P integrative. And LP is a space of P integral measure, which is equipped with the semi-norms indexed by nu. So the semi-norms of index nu is the limit of the integral of fnp semi-norms in nu as n goes to infinity. And this is the limit for every P integrative sequence. And there is a theorem, which is important, which says that the limit here exists and does not depend on the choice of the sequence Fn. And this is proved in again, in the book Integration. And at the end, if I have time, well, maybe I will give hints from proof. It's not so complicated, but it needs some time. Okay, and I pass on for L infinity because only thing is that we have two conditions instead of one. That is, the sup of Fn semi-norms nu is finished, and it is a semi-norms on each compact subset, and it goes the same when you say the nth. Okay, but there is an important thing, that is LP is a Neumann space. Okay, we want that to know. LP is a Neumann space for P finite or not. And this is proved again in integration. And now that we have LP, we can construct the space WMP. Classically, the space WMP is the set of F such that all its derivative d beta f are in LP for m if m is positive, and it is equipped with the semi-norms, the classic semi-norms of all the derivative with the power p. And for infinity, it's not the sum, it's the sup. And this is again the Neumann space. And if we consider negative m, f is the sum of the derivative of some LP function. So this is right. And it is equipped with a semi-norm, which is the infimum for all the possible decomposition of f in f beta, in sum of derivative of f. F is the sum of the derivative of f beta of n. Okay. So we have the space that we need. Now, the question is, we have construct the space LP, but is this space the same thing as usual if the space E is a Banach space? So we consider a function f, which is a measurable P integrable function, f in LP, L cursive. And we consider f dot, which is a class of functions which are almost equal to f. This is, in fact, a classical LP space. In fact, the LP space may be extended with values in a Fresher space. That is a space which is provided with a denumberable set of semi-norms. this is not too difficult. This follows the same construction as usual, but with some refinements. But if E is not Fréchet, this absolutely fails, because it is based on Egorov theorem, and Egorov theorem clearly does not extend to non-Fréchet space, if it is yet. But if we can define to this F, we can associate a measure F bar by the classical F bar applied to phi, where phi is a continuous function with compact support, is the integral over omega of f dot phi. Or it is the same that on the integral of f phi, because it is defined as that. And we can consider the space L bar P is the set of this measure. And this is an important theorem that says that if E is a Fréchet space, and if omega is open, that is absolutely crucial, the class of function consider with coincide with the integral measure. That means that LP bar is the same as LP for P finite. And if P is infinite, this only holds if E is a Banach space. We have not, I am not able to prove it in the case of Fréchet space. And the space F dot, to F dot we associate F bar, it is an isomorphism from the space LP into dot LP into LP. It is the same, in fact. Up. So, in fact, we have the classical space. If we consider the space defined with values in a Banach space, in a Fréchet space, and on an open set. Why on an open set? Because if it is not open, if it is only measurable, we, for example, if Q is measurable, the function with compact support on Q, there is only the zero function. And so, or if we consider omega Rn minus Qn, we have also zero. So we have no measure. But it is the first advantage that it is a space of distribution. And when we do PDE, it is interesting to have distribution more than class of function. And the second and the more interesting advantage is that it allows E to be a Neumann space. So it allows to be LP1, to be HM weak, to be a lot of things. And the advantage of class of function is it allows omega to be a measurable set. And the second advantage is that it provides dominated convergence that gives some more interesting results. So we have some more interesting results in the case, well, okay. But quite all the usual results on LP space extend to the space LP with values in a Neumann space. There are 300 pages that which do that. And so what we do, the ultimate question is what we do if we want to integrate something which has not values in a Neumann space. what we can do is to embed E in its sequential completion E hat, and this exists. So, given a semi-normed space, there exists a sequential completion that E hat, such that E hat is a Neumann space that contains E, in which E is dense. The semi-norms of E hat extend the semi-norms of E, and there is no sequentially complete proper subspace of E. There is no other. It is the smaller one. And so we can define F with value in C of omega with value in E hat, and then we can define its integral that has a value in E hat, and which can define the derivative in the sense of distribution, which are in values of distribution, which are in the space of distribution. We can also check that F is a sequential. It is not necessary, in fact, that a space F is a sequential completion. It suffices to embed E in a space which is a Neumann space, such as L1 weak is embedded in the space of measure, and L infinity, here there is a mistake, it is star weak. No, L infinity, sorry, L infinity weak may be embedded in L infinity star weak, which is a Neumann space. And so all goes on. So now I see if there is some time. Yes, maybe I will give you some hints that prove that the integral measure exists really. So we consider a regularizing sequence of function rho n, which are in a small ball, and of integral 1. And we consider a localizing function which is almost everywhere 1, and is only cancelled in a small near the boundary. And we define the regularized Rn of f, such as f is multiplied by alpha n, and then it is convolved with rho n. And so we obtain Rnf, which is a function with compact support, which is uniformly continuous. And due to the Young inequality, we have the integral of the regularized that are less than the integral of the function when the power of the power p. And as n goes to infinity, we have also Rnf go to the f, the regularized go to the function. And the map Rn is continuous from M into the continuous function, from the measure into continuous function. And the hard point is only to see that if Fn goes to, is a sequence that goes to 0 in the space of measure, and if it is a Cauchy sequence for the power p for every semi-norm, then the integral of Fn power p for every semi-norm goes to 0. And to prove this, we decompose Fn in Fn minus Fl plus Fl minus the regularized of Fl plus the regularized of Fl minus Fn plus the last term. And we see that if epsilon is positive, there exists a sequence such that Fn minus Fn goes to 0. So I can choose n such that it is smaller than epsilon over 4. And then the first time, in the right-hand side is bounded by epsilon over 4. From 3, I go again, 3 is a convergence to the function. From 3, there exists k, such that the second term is bounded by RK FL minus FL is bounded by epsilon over 4, if L is fixed. And from 2, the third term is bounded by, this term is bounded because the regularized have seminorms that are less than the initial, so it is the same. And so all the 3 first terms of the second of the right-hand side are less than epsilon over 4. And for the fourth term, we use the support of RK of Fm is included in some compact subset, because k is given. And the integral of Rk over Fm is smaller than the measure of Kk, which is the support, and the sup of Rk or Fm. But as m goes to infinity, then Fm goes to 0 in the set of measure. And so, due to the continuity, this sup goes to 0 uniformly. And so, all goes to 0, and we have our lemma. And now it is quite finished, because the measure f that possess a p-integrative sequence Fm, they form obviously a vector space. The sequence Fn over p has a limit, since due to Minkowski inequality, the left-hand side is smaller than the right-hand side, and the right-hand side has a limit that does not depend on the choice of the integrative sequence. And Fn minus Jn is a p-integrative sequence that of the null function that we see in the previous lemma. And so these go to 0, and so the right-hand side of the above inequation goes to 0, and so the left-hand side again. And so we finally have what we want. It's quite time. And so I will just give you some references, because maybe the proof was a little rapid, but it is only to see you that it is not really hard. It does not appeal to very difficult things. So I have written a lot of books. The first book is named Banach, Frechet, Hilbert, and Neumann spaces, and this is available. So this defines mainly what is a Neumann space and give all the properties that are required. The second space is continuous function. The third space is on distribution, and it is an important book also, because it gives all the property of distribution that we need with value in a Neumann space. And the fourth book, which is in press, I have given it to the editor this afternoon, so it is not available because it reads it a lot, and but in some months it will be available. The next book, which I am writing, is for Sobolev spaces, with all with values in an Neumann space. The following book is on the traces, again in this space, and the final book is on PDEs, and it is almost written. But first, I need to read the space, the space on the book on Sobolev spaces and on traces. And if you want to be advised of the next volume publication, you can send me a mail, and I give you all the information. Yeah. And so it's a pleasure to. Muchas gracias por su atención. Muchas gracias a Juan Bautista Limaco Ferrell por la oportunidad to exponer todas estas cosas this afternoon. Thank you very much.
Thank you, Professor. Gracias. Thank you. Let's open for some questions or comments. Juan, can you open the audio for the audience? Ask questions or comments. Todos podem comentar. Todas as pessoas podem comentar, se querem. The chat is open as well. I don't have any question, but I just have a comment about your book of distributions. It's a very good book, and I use it a lot with my students. This book, okay? This book is
Which book?
Distribution. Your book of distribution. This one.
Distribution?
Yes. It's
Yes.
a nice book, and well, all of the students is in the audience maybe need to see this book because it's very, very nice.
Question in chat?
Questions in the chat? Let me check. Yes, let's see. Okay, Professor Cavian is here. Thank you. Vitor Hugo, thank you, Professor Simon, for your nice talk. Is there any well-posedness result for the hyperbolic equation, such as the wave equation for source or initial data in Neumann space? The question of Vitor is if you have some well-posedness result for the wave equation in the Neumann space. Do you have some reference or?
No. In fact, no. I have not precise references because, in fact, it does not really change the results that are known, but it allows first of thing, it allows to use something more simple. That if you can use this space, and for an example is for the equation, the stochastic equation that was done by Groniuk. He did a lot of work to construct a space and to see that he has some possibility, some natural qualities, but in fact it is the space usual and all is working, and so he can use it. So it allows to do something more. The main thing that it allows is to use unbounded domain, because here you have values in spaces that are only locked. And so it is not a Banach space. But it is in reality it is a fresh space, and so you can use the usual space with values in a fresh space.
Okay. Okay, Vitor, your questions. Lohan, excellent talk, Professor Simon. Carlos Aparcana, muchas gracias, Dr. Simon. Vitor say, okay, thank you.
Okay, thank you very much. I close my partage.
Yes, please, thank you, Professor. Juan, you can
Okay.
Thank you, Roberto, and thank you a lot, Professor Jacque Simon, for your amazing talk.